Alright, hello everybody, and today I'm going to be proving a very interesting polynomial identity, which says that if you take any polynomial of degree n, where our n is greater than 2, so our polynomial is a quadratic or higher, and if you take all the roots of our polynomial, I'm going to call the roots zi for now, so Pn of zi is equal to 0. Then if you take the sum of the reciprocal of the derivative of the polynomial, evaluated at all of its roots right here, the answer is going to give you 0. So what exactly does this mean right here? Let's take the smallest case we can get, which is a quadratic. Let's say it has a real roots, so we have 2 roots right here. You see 1 over the derivative at a pole, that's kind of like the normal line, because if you place negative right here, that's going to give you the gradients of a normal line at a pole. So if you take the gradients of normal right here and another gradient and a normal right here, if you add those two gradients together, you're going to get 0. So that's the general case. Let's say for a cubic, if you have 3 solutions, like so, if you take the normal here, and the normal right here, if you add all those gradients together, you're going to get 0. So sometimes for the polynomial, you might not get n roots because some of them might be complex. That's why we're considering all the complex roots as well. So just to be clear, using the fundamental theorem of algebra, I think it is, if you have a polynomial of degree n, you're expected to have n roots. So that's why here we're summing from 1 to n, because we need to evaluate this thing at all of its roots. So how can we prove this result right here? Since we're considering all the complex roots and everything as well, we might as well use complex analysis to do this. And after a lot of pondering, I realized that we can use a very nice result from complex analysis to prove this thing right here, namely the residue theorem. Because if you, for example, take the contour integral of some function, let's say f of z for now, dz, and that contour is some squiggly thing that encloses a bunch of poles or whatever, it's going to evaluate, the value of this contour is going to evaluate to 2 pi I times the sum of the residues. And depending on how many poles you have in here, you're going to sum that many residues together. Notice this sum of residues right here kind of matches up with this part right here, because if we can identify this inside of the sum right here as some kind of residue, then we can maybe use this residue theorem for it. So how can we get started right here? You see we have this 1 over p prime then at zi right here, and this was kind of like my first thought process, because we know Pn of zi is equal to 0. So if we take 1 over Pn of zi, it's actually going to be undefined because we're dividing by 0. But usually when we calculate these residues, we like to use L'Hopital's rule whenever we have like a 0 divided by 0 situation in order to evaluate the residue. And in using L'Hopital's rule, we differentiate the top and we differentiate the bottom, and we get some kinds of p prime like so, which matches up right here. So I want to somehow generate a 0 over 0 situation for this fraction. So first of all, we have this denominator sorted out, and I'm going to be writing quite a trivial statement, but this will be very important later on, namely that zi minus zi is equal to 0. Because now what we can do using these two equations right here is we can put them together. So if we have zi minus zi on the top and Pn of zi on the bottom, we're going to generate a 0 over 0 situation. And let's actually replace the argument of this polynomial with an actual variable. Let's just call it z for now. So we want to take the limit as our z approaches zi, and that's going to give us a 0 on the denominator, and we want to also generate a 0 on the top as well. So what we can actually do is we can replace this first zi right here with just the z. So when this z right here approaches zi, we're going to get zi minus zi, which is 0. So if we take the limit as z approaches zi of this whole thing right here, it's going to give us a 0 over 0. But since we have this case right here, we can use L'Hopital's rule for it. So all we have to do is differentiate the top and differentiate the bottom, and we're going to get the limits as z approaches zi of, well, the derivative of the top, it's just going to evaluate to 1, which is really quite nice because it matches up right here. And if we differentiate the bottom right here, we're going to get Pn prime of z. Okay, and taking the limit as z approaches zi of this thing right here is going to land us at 1 over p prime n of zi, which is really quite nice. And just one quick note right here, we want our zi to actually be a simple zero or a zero of order 1. Because if this zero is of a higher order, then p prime of zi might actually be 0 and this thing might actually explode to infinity. But I'm quite sure if a polynomial has multiple unique zeros, then it's not possible for this to happen. But yeah, I don't think that's too important to worry about. So following on from this line right here, we know that p prime n of zi, which is this part exactly right here, that can be expressed as this limit right here. And so this right here is actually matches the definition of the residue, because if we have the residue of some function f of z at a point zi, for example, then it's defined to be the limit as z approaches zi of z minus this point right here, so z minus zi of f of z. And you can kind of see that in this expression right here, because we have this z minus zi, which is exactly this part, and we can say that our f of z is equal to 1 over pn of z. So what we can actually do is we can say that this whole entire limit right here is the exact same thing as the residue of 1 over pn of z evaluated at zi. So we know this residue thing right here, it's going to give us 1 over p prime n of zi like so. And remember, in this expression right here, we're trying to sum up all of these from I equals 1 to n. So if we sum this thing from I equals 1 to n of 1 over p prime of n zi, then that's the exact same thing as summing up all these residues right here. So if the sum of the residues from I equals 1 to n of 1 over pn of z at zi. So basically what we just found right here is we found that this thing we wanted to prove right here, that can be expressed as the sum of residues right here. And as I said before, you usually see these sum of residues when you're evaluating contour integrals. So it would be very nice if we can somehow turn this thing right here into a contour integral kind of. Because if we have the contour integral over some contour c of, let's actually take this function for now, 1 over pn of z, it's going to be equal to 2 pi I times the sum of the residues of 1 over pn of z, so 1 over pn of z, evaluated at a couple of its poles. And let's say its poles were zi, and we actually want to hit all of the poles, so I going from 1 up to n. But the thing is, if we want to be able to calculate the sum of the residues at all of its poles right here, our contour has to be able to enclose or capture all of the poles. So what do I mean by that? Well, first of all, we know that this pn, 1 over pn right here, will have n poles, because we know pn of zi, one of its poles, it's going to give us 0. So if we have 1 over pn of zi, then it's going to give us a singularity. So our contour, let's say our pn had a couple of poles, whatever, our contour has to be able to capture all of those poles right there. If it only manages to capture some of them, then we won't have this expression right here. We'll only be summing up part of the residues, but we want to be summing up all the residues that we possibly can. So that's why our contour has to enclose all of these poles right here. So how exactly can we come up with a contour that can do this? Well, a solution is to consider some contour of radius r like here. So we'll call this contour c with a radius of r. And what we're going to do is we're going to take the limit as our r approaches infinity. Because if our r becomes bigger and bigger and bigger, it's going to be able to capture more and more, and hopefully all the poles of this function right here. And you might be wondering, well, if we take the limit as our approaches infinity, then the value of our contour won't be consistent or whatever. But the thing is, if you use Cauchy's integral theorem, I think it was, as long as you enclose all of the poles of the function, the value of the contour will still be the same. So even if our contour had a finite radius, but it could capture all of the poles, the value would be the exact same thing as if the radius was going to infinity, because, well, it's still capturing all the poles. So that's the idea. And basically what we're going to show from this result is that the value of the contour, so the contour integral over C, actually goes to 0. And the nice way to do that is to actually use Jordan's lemma on this to show that this integral goes to 0. And that's what I'm going to be doing in the next part of this video. So we know that we're going to have a circular contour traversed in the positive direction, and I want our r to approach infinity. So let's set this up right here. So let's take the contour integral over C of 1 over Pn of z zz. So in order to do this right here, let's actually call this integral I for now, just so we know what we're dealing with later on. And let's first of all introduce a new parameterization right here, because we already know the path of our contour, so it would be nice if we can parameterize it a little bit. So if we introduce a new substitution, I think that's the best way to go about it. If we let our z be equal to r times e to the I theta, where our theta goes from 0 to 2 pi. So this parameterization makes sense because we're going on a circle, so e to the I theta of radius r right here, and our theta is going from 0 and it's going anti-clockwise all the way around to 2 pi. So if we do this substitution, it's going to work for the parameterization of this path right here. So if we differentiate both sides, our dz is going to become I r e to the I theta d theta, and now we can plug all this information in. So our I is going to be equal to the integral. Now instead of our contour, we're going from 0 to 2 pi now, so 0 to 2 pi of 1 over Pn. Now our z is equal to r times e to the I theta, and then our dz is going to be I r e to the I theta d theta, like so. It's now what I want to do from here is I want to start estimating this integral a little bit. So we want to somehow bound this integral. So to do that, let's take the absolute value of this integral. So absolute value of I, it's going to be the absolute value of this whole entire integral right here. So the absolute value of integral from 0 to 2 pi of 1 over Pn r e to the I theta, I r e to the I theta d theta, and another absolute value. So what we can do from here is we can start using inequalities a little bit, because notice we have the absolute value of an integral. So what we can do is use the integral inequality to say that this whole entire thing is less than or equal to the integral of the inequality. So this is going to be the integral from 0 to 2 pi of the absolute value of the insert. So we're going to have 1 over the absolute value of Pn r e to the I theta, absolute value, and then we're going to take the absolute values of each of these parts right here. So absolute value of I is just 1. Absolute value of r, let's actually bring that out to the outside because it's still going to be r. Remember, r is some positive number right here. And absolute value of e to the I theta. Well, e to the I theta is just some complex number on the unit circle. So the absolute value of that is just the distance it is away from 0, which is 1. So we can ignore that, and we're going to have d theta like so. Alright, so we have this integral right here. And now what I want to do is I want to take a look at this Pn of r e to the I theta right here, because we want to be able to further bound this thing a little bit. So if you take our Pn of r e to the I theta, and you put that in absolute values, we want to be able to somehow estimate this further. So that means we need to find upper and lower bounds for this thing right here. Because notice that we're going to be later letting our r go to infinity. So our r is going to get very, very, very big. And for big enough r, we can actually bound this thing. Because remember, our polynomial is of degree n. So for big enough r, we can say that it's less than or equal to some constant c times r to the n. And why does this make sense right here? So if you just imagine having real inputs right here, I don't think it really matters because we're taking absolute values anyway, so it's just going to turn it into a real number. If you have some nth degree polynomial, so let's say, I don't know, quartic for example, and you let r get very, very, very big, then you can actually bound this graph right here with some upper bounds c of r to the n. So we can actually bound this by some really big quartic, right, like so. And that's only for really big r. And similarly, we can say that this is less than or equal to a lower bound. So at the very start, I said that our n was greater than or equal to 2. That means we can find a lower bound because our n can't get smaller than 2. We can say that it's going to be always bigger than some constant, I'm going to call it a now, of r squared. Because you can always find a quadratic, a r squared, that is less than our p of n right here for really large n. So even though we have like stuff hanging off the ends right here that might not always be less than or greater than our p of n, for really big r, our polynomial right here will always stay in between these two lines. So you might have some like crazy looking polynomial of degree 8. Let's see if I can draw that. So 1, 2, 3, 4, 5, 6, 7. I think that's an 8th degree polynomial. For really big r, you can always find an upper bound for it, and you can always find a lower bound, so something that goes a little bit lower. And this blue line right here, our polynomial will always stay in between those two lines right here. So this is our a r squared, and this green line right here, that's our c r to the nth power. So using that little idea right there, we can agree that we can bound this polynomial right here. So after we've done that, we don't actually have this exact thing in this integral, we have its reciprocal. So if you take the reciprocal of this thing right here, so 1 over the absolute value of Pn r e to the I theta, when you take reciprocals like so, you're going to flip these inequalities right here. So this is going to be greater than or equal to 1 over c r to the n, and this is going to be less than or equal to 1 over a r squared. And since a and c are just random real constants, let's just bring them up to this top. It really doesn't matter what constants they are. So the main part we're going to be focusing on is this boundary right here, because 1 over this polynomial is going to be always less than or equal to a over some r squared. So if this thing right here, this thing inside the integral, is always less than or equal to a over r squared, then we can further bound our integral. Because if the integrand is less than something else, then naturally the integral will be less than or equal to, so the integral from 0 to 2 pi of 1, actually a over r squared, d theta, like so. And notice that a over r squared, that's just a constant, so let's bring that to the front, and we're going to cancel out these r's right here. So we're going to have a over r times the integral from 0 to 2 pi d theta, which is going to evaluate to 2 pi. So after all of that work, we found that the absolute value of I, like so, is less than or equal to this integral right here, which is less than or equal to this thing, which evaluates to 2 pi a over r. And well, remember, we wanted to let our r approach infinity. So if we take the limit on both sides, so the limit as our r approaches infinity of the absolute value of I, that's going to be less than or equal to the limit as our r approaches infinity of 2 pi a over r. And well, that limit as the r gets really big, it's just going to vanish off to 0. So that means that the limit as the r approaches infinity of our I is less than or equal to 0. And notice that this absolute value right here is always positive. So the only way for a positive number to be less than or equal to 0 is that if this positive number is 0 itself. So we can kind of ignore these absolute values right here, and we can say that the limit as our r approaches infinity of our I right here, our contour integral, it's going to be less than or equal to 0. But since it's a positive number, we can say that it is equal to 0 itself, because the only way for a positive number to be less than or equal to 0 is if it's 0 itself. So that is pretty much it for this part actually, because we've just shown that in the limit as our r approaches infinity of our contour right here, it's just going to be 0 in the very end. So this integral right here, in the limit as our r approaches infinity, it's just going to give us a 0. So overall, what did we just prove right here? We showed that this contour integral in the limit as r approaches infinity goes to 0. And since we're considering the radius of our contour going to infinity anyways, we can say that this whole entire integral is 0. So overall, we showed that 0 is equal to 2 pi I times the sum of the residues, so sum from I equals 1 to n, of 1 over Pn of z at all the zi's. And well, 2 pi I is not equal to 0, so we can divide both sides by 2 pi I. So we showed that 0 is equal to the sum of residues of this thing right here. But remember, this thing right here was also the exact same thing as the sum from I going from 1 to n of 1 over p prime of zi. And if you need me to prove that again, we can just use the definition of the residue. So this is the sum from I equals 1 to n of the limit as z approaches zi of z minus zi times the function, so 1 over Pn of z. And while this numerator will go to 0 as our z approaches zi, so will this denominator. So if we use L'Hopital's rule for that, we're going to have the sum running from I going from 1 to n of differentiating the top. We're going to get 1. So we're going to have 1 over the denominator differentiated p prime of z. And since now we don't have any problems with the zeros or anything, if we directly plug zi into this thing right here, we're going to end up with this result right here. So basically, using complex analysis, we showed that the sum of the reciprocal of the derivatives of a polynomial evaluated at its poles is equal to 0. So that is my proof for this little polynomial identity right here. So yeah, really cool identity. It was quite fun working out a proof for this. But so yeah, hope you guys enjoyed this video, and until next time, have a wonderful day. Yeah, I'll see everyone later. Bye bye.